Thank you for the participation to all of the enrolled persons. Now we start the webinar. The title is Does Deep Drilling Need a Revolution? This is strictly connected with the DeepU Project. It's a European project that aims to develop new technologies based on laser and cryogenic gas to drill faster and cheaper. There are different colleagues that participate to the project that will give us not only information about the project, but even a sort of a state of the art of the drilling. Maybe I will start now with the leader project, Luc Poquelet from Red company. This is an Italian company. That's one of the partners and the leader project of the DeepU. Now I'd not lose other time, and thanks, Luc, for your presentation of the project.
Okay, thank you, Antonio. Welcome everybody, and thank you for your interest in this webinar. My name is Luc Poquelet, as Antonio said, from Red SRL. We are the project coordinator. We have taken over the coordination from the University of Padova in the middle of the project. And I will give you a short introduction of the DeepU project itself and introduce the agenda of the webinar with the different speakers. You see the participant logos on the first slide, and I'm now moving to the second slide, which gives you an overview of the project objectives. The intention being, so we are 7 partner organizations. We had the pleasure to win a hop-on widening project so that we had the University of Technology of Wrocław to join the 6 originating partners for the project. And the project is about using a laser to drill, to loosen the rock and to flush with cryogenic gas the rock residues to the surface. And this technology would especially be interesting at higher depths where there are rock formations which are very hard and abrasive to drill. And it also is the intention to go to closed loops with this technology. Finally, the intention would be, which will become clearer when we explain the technology, that we aim to reduce the costs of drilling, and you will see why they could become lower, and which we could also go to depths for sufficient temperatures so that we can go to geothermal anywhere. The project develops basically the drilling head and the drill strings, the shafts for the drilling. We validate the technology at lab scale, so we are not yet going to the field, but we already explore the legal and environmental aspects so that we are ready to go to the field, because this is a new technology and we need authorizations for that. This will also be covered in this webinar. And we will also do simulations and cost assessments to have the first preliminary indications on potential business plans for this technology. The technology itself is, you can see that on this slide, it's a laser beam which regularly gets refocused through lenses in the middle of a drilling shaft, which then opens up at the bottom to heat up the rock and to spall, which means heating up the rock so that it expands and that it goes into pieces. It will become clearer also in one of the presentations. And then with the cryogenic gas, which is at the sides of the central tube of the drilling shaft, it's introduced to cool down and to pneumatically transport the drilled particles up to the surface. So this is in a nutshell the technology. Since this is a non-mechanical drilling technology, so it's a non-contact drilling technology, we expect that we would be in continuous drilling operation, contrary to conventional drilling, where you regularly need to trip up and down to replace the drill bit, which gets consumed by the drilling, and that would improve let's say the rate of progress on an hourly basis, and this would also reduce drilling time and cost. There is the possibility, we are exploring that through the heating of the walls of the borehole and the subsequent cooling by the cryogenic gas, that we could form glazed layers, which in certain circumstances could avoid the casing, and through that also reduce time and cost. So this is in a nutshell the technology and the objectives. The team itself, I already explained quickly that it's focusing on developing the drill bit, developing the drill string, simulate the conditions and the gas flushing system, do a lab test at small scale, and then analyze the laser rock interaction of the drilling process, followed by exploring also what standards and regulatory integration we need to have to bring this technology into the field. And then as I already explained, the exploitation planning, the IPR aspects, next to the traditional work packages on communication and management of the project. The webinar agenda will be so the first after me, the first speaker will be Kevin Mallon, who is a very experienced person in deep drilling technology, and he's been around from I think from the 70s. So he has lots of experience, and we will cover the state of the art. Then Pavel Slupski from the University of Padova, who has witnessed and guided all of the lab tests. He's done also the analysis of the laser rock interactions, and he will talk about those aspects and the laboratory results. Whilst Professor Maciej Korowski from the Wrocław University will talk about the cryogenic aspects, which were crucial, as well as the simulations to progress this technology. Finally, Riccardo Pasquali, also from GeoServe, will cover the environmental and regulatory aspects. I wish you a very good webinar, and I leave the floor now to Kevin for the second part. Thank you for your attention. I'll interrupt the condivision so that Kevin can put up his slides and start his presentation.
Thanks, Luke. Please, you can after Kevin follow as convener the process of all the lectures. Thank you. I'm waiting for the sharing of the slides from Kevin.
Antonio, maybe you can load the slides and then follow move them when Kevin speaks eventually, if he would have problems.
Okay, Kevin, I share my screen with your slides.
Yeah, sorry everyone. For some reason, I find it very difficult to share in Zoom. So anyway, welcome everyone. Good morning to most, and good afternoon to Taras, I think, who's in Western Australia. So welcome everyone. The reason for the title: does deep drilling need a revolution? Currently, all drilling revolves or rotates their drill bits. With the non-mechanical, we're not aiming to rotate. So it's a little bit of tongue-in-cheek title. Next slide, please, Antonio. So this is probably telling you what you all already know, but mechanical drilling really relies on us putting mechanical energy into a drill string to either churn up soft rocks or break harder rocks. So we apply weight, we rotate it, that sort of breaks the formation into smaller particles or chippings. They are then flushed up the hole. We rotate the bits because obviously we need a round hole, and so we need to clean them. And those cuttings get moved to the surface either by fluid or air or sometimes gas that we use, and then that leaves a hole in the ground, hopefully. So the energy inputs are for lifting, lowering drill strings, rotating, motors in the drill string as well, pumping, compressing air, however we're going to do that system. So the one key outcome always is to make sure we're left with a usable wellbore. Interesting, I was on a call yesterday with another drilling company, not for geothermal, and they were getting quite high rates of penetration, but their actual overall rates were quite low because they couldn't clean the cuttings. So we had to make sure that when people say, oh, we're drilling at 60 meters an hour, is that really what they're drilling at? Or are they really only drilling at 10 meters an hour? Because by the time they have to lift off bottom, they have to clean the hole, they have to do wiper runs to make sure the wellbore's clean. That's when we need to understand what is our rate of progress overall. So, thank you, Antonio. The main drilling technologies currently, there are one or two sort of oddball things around, but generally they're either rotary percussion, normally we call them down the hole hammers, which are powered by compressed air or fluids. There's the roller cones, which everyone's familiar with, the Haratus back in the early sort of 20th century perfecting roller cones, and then the fixed cutter. The fixed cutter bit has been around forever. It was probably the first time we started making holes, rotating drill strings. It would have been a fixed cutter bit. And we'll go on to talk about the fixed cutters in a minute, because they sort of made a comeback recently in different ways. Next slide, please. Right, down the hole hammers. These have been around. I mean, Simon Ingersoll invented the down the hole hammer back in 1869, something like that. It's improved exponentially, really, with the ability to compress air. The problem with compressing air is it's highly inefficient, it's very expensive, and so you're quite limited economically to the depths you can drill. You're also limited really by some of the formations, the weaker, less stable formations don't like being drilled with air. So, it's like everything. And when we talk about state-of-the-art drilling, there's no one drilling method which will actually do everything. So it's more like, I compare it often to going out to play golf. You don't just take one club to play golf. You take a selection of golf clubs, so you can play the ball depending on where it is on the golf course. So and this is the same with drilling. So it's not a comparative thing that we're doing here. We're just showing you really what is out there. I've used Centre Rock because I do a great deal of work with Centre Rock. They are also very, very famous because they actually made the drilling system that rescued the Chilean miners. So they have a sort of a place in history and in Hollywood, actually. So next slide, please. These are all familiar. I mean, these are down-hole hammer bits. These are, in fact, Copco bits from our oil field days when we did a lot of drilling in the shale gas in northeastern USA. You can see the various shapes of the face. Those are really so we can direct air flush. And one interesting thing that's come about a lot recently is the increased use of the computerized flow dynamics. So we can actually model the flows on these bits a lot better for hole clean. And that's not just the air hammer bits. You'll see it with the water hammer bits as well. And when you see a water hammer bit, quite often you don't know they're any different. And some people, like myself, in fact, we save money by using ordinary sort of air hammer bits in water hammers because they are, for some reason, they are just cheaper. So you'll see the top left-hand one there. It's the actual face of the bit is drilled out, ready to take the inserts, and it allows us really to quickly on the fly change what we're trying, sort of to break the rock. We can change where we put the buttons, and that's quite a sort of useful thing, and it can be done very quickly. So those you'll see them as blanks, and then they just drill and insert the buttons, and the same with the top right hand there. The middle one at the bottom, you'll see the buttons have been inserted. These are hemispherical buttons. If you look carefully, the buttons on the outside are larger than the buttons on the face of the bit. The gauge buttons are the ones that wear out first, because obviously they are in constant contact with the rock as they're rotating. The face buttons, you'll hear all drillers and that talk about indexing. Each time you rotate, you want those buttons to hit a new fresh piece of rock. So, rotation speed is very important to optimize down the hole hammer drilling. So you're not sort of dragging the bits as well. So if there's any questions, just sort of, we're going to have a question and answer session at the end. So you'll be able to sort of come back to these. Compressed air. These are sort of, we've been compressing air for a very, very long time. It's getting more and more efficient, as I say. The big issue with compressing air is it takes a lot of energy. So, I mean, the top one, that's a twin air compressor from Atlas Copco, used both offshore and we use them onshore as well for hammer drilling. That's that one is 1600 kilowatts. So that's 1.6 megawatts of energy in that container. So it's it uses a huge amount of energy to compress air. So and we'll talk in a minute about the why we use water. At the bottom, that's a hurricane booster that basically takes the air out of those compressor and boosts the pressure. So we can get up to, and in fact, I think the highest ones are now are about 7,000 PSI boosters. So that air pressure is very, very important to hammer drilling, but you have to match the sort of the amount of air you put in as to the pressure you can use. Otherwise, it becomes super inefficient. It's like having too much fuel going through your engine and not burning it all. So it's a very it's a fine balance, and lots of drillers never fully understand that balance, and so they waste a huge amount of money on fuel by not usually balancing that sort of fine thing between pressure and volume of air. Thanks, Antonio. These are the water hammer from Vasara. This is the Vasara hammer. It was originally developed because in the LKAB in northern Sweden, who mine iron ore underground, the rock is very hard. The one thing they have as well, they have lots of water in the mines. So it was developed around, well, we got a lot of water, let's compress water, let's look at how air hammers work, and then we'll use high pressure water to power these hammers. They are great. These water hammers are really very good. They drill very quickly. They have a lot of vibration, which is a big issue for some of the smaller rigs. The downside of them is they want potable water. It's got to be very clean water. You can't have any suspended solids, sands. You can't put mud through them. We do run polymers through them, but even then, it's not super efficient for water hammers. The one thing that we've used them for offshore quite a lot for drilling holes. In fact, in this major roadway on the sort of west coast of Norway from Bergen to Trondheim, we've done lots of drilling offshore with these water hammers, where we just run seawater through them. Seawater is not the best because it does have some suspended solids in it, but the cost, the rates of penetration we get with these hammers compared to conventional drilling methodologies, particularly in the granites up in Norway there, offset the cost. So these really are almost single hole throwaways. So we drill the hole and then dispose of the hammer. So there's a few other suppliers of water hammers now, particularly I think Numa hammers in the US, and Drill King, which is WAI out of Germany. And so there's a lot of technology coming in around the water hammer. The one thing I will say is generally people are looking at the smaller sizes because of the issue with having clean water and the need for clean water. So they sort of tended to concentrate on the smaller size hammers. Thanks, sir. Right. I want to say this is a beast because it is. I've been closely following Strata now for 11 years. So the great thing about this gives you all the advantages of compressing a fluid and the efficiencies of doing that, but they've developed a new system, and it's quite innovative, of using a dual circulation, so they can put heavy, dirty fluids through the hole to clean if they need to, and fresh water to run the hammer. So we're not getting the wear that you would see in a standard circulation water hammer. They've done a lot of dirt, and I know Julian and Taras are online at the moment. So if you've got any particular questions to answer, because it's very simple in how it operates, but there's a lot of technical things behind it that you may want to discuss with directly with Strada. As I say, I've been following this very closely now for a long time, so it's a great method for drilling in harder rocks because they have a water cleaning system or a mud cleaning system as well. You don't have the high demands that you would have with a direct clean flush water hammer. So I think this in lots of ways for the granite drilling and the harder drillings, this will probably be quite a very effective method of drilling. No real the only real downside of it would be because it uses a special drill string. Other than that, it's a great way of drilling holes. This is from GeoVolve. GeoVolve is part of Hydrovolve, and Hydrovolve make jarring links. So if you get your pipe or something stuck down the well, you run in a jarring link, or sometimes you'd actually run a jarring link as you're drilling. So if you do get stuck, you can jar with the thing. This is a sort of hybrid between standard rotary and percussion drilling. So they'll run a percussion bit on the end, and the system, there's a piston in there, the jarring piston, which adds additional energy to the bit. Some years ago, I mean, the actual concept's been around for quite a long time now. Atlas Copco back in the day, they ran a thing called PARD, which is percussion assisted rotary drilling, where they took a down the hole hammer, they machined special chucks, so you could actually screw conventional rotary bits into them, and you drill with a tricone. They only use tricones, and a down the hole hammer. That was basically developed for quarrying or mining applications, surface mining applications, where they wanted to try and drill faster with tricones. It wasn't a great success, to be honest, mainly because the impact energy of the hammer was way too high for the bearings on the tricone, so there was a lot of bearing failure. So it's still around. Some people do use it, but it's no longer state of the art. The GeoVolve one it's a good hybrid. The advantage with the GeoVolve one, it runs in any drill string you want it to do. You can put it into any bottom hole assembly. Again, if you Google GeoVolve or Hydrovolve, you can get a lot more details. I don't want to go into too much detail because it's huge. There's an awful lot of technology behind all these things that we're looking at, which is best. You know, if you are really interested in looking at these technologies, it's better to go and concentrate on that one rather than me go, this is what you need. So the GeoVolve one it's been a good opportunity for those drillers who are not used to down the hole hammers, and they have done quite a lot of work, interestingly, in Ukraine recently. So it's a good system, And if you just onto the next slide, please, Antonio. There's just that's just one case history. If you look on the bottom right, you'll see the types of bits that they're using, which they're a hybrid PDC bit, which we'll talk about in a minute. And if you're interested, and you talk to Strata, Strata's got a very interesting, and I mean it is very, very interesting concept around using their hammer and PDC bits. And I urge you to talk to them directly, because it is something very different to what has been done in the past. And to be honest, it was probably by coincidence they came across it rather than, thinking, and they've come up with a great concept in what they're doing with they're using a PDC bit. Okay, thanks, sir. Here we are. I hate to say it, but these, since Howard Hughes, way back in the day, in Bakersfield, California, secretly worked on making these tricone bits. They are still very much used in our industry. So although we call them, they're still state of the art, it's stuff that we've been using now for well over 100 years. I mean, almost 130 years now. So it's very simple technology. You just load it with weight and you turn it and turn it and turn it, and it will break rock. The bit on the right is for softer formations where they gouge into sort of clays and mudstones. We call them, or the deeper drilling industry tend to call them tricones. The shallower drilling industry, they tend to call them roller cones. But it's age-old technology. And again, what's improved here is the materials that they use. And you'll see the bits on the left are all using tungsten carbide inserts, and the bottom bit on the left is using a PDC enhanced, so it's got a diamond coating on the buttons to increase the sort of longevity of the buttons. Again, because they're in contact with the rock as they're rolling, you've got a wear factor. So the buttons wear out and become less effective. And you'll see on what we call the shirt tails on the sides, you'll have what they call gauge protection to maintain both the gauge of the well and try to protect the buttons themselves. You'll see where they've got flushing holes. In there, you can enhance your hydraulic system from the pumps by putting in smaller nozzles, so you get a jetting effect. If you just want full flush, you take those nozzles out and just get as much fluid as you can through and back up the annulus. With all these types of bits, and with the water hammer and the mud hammer bits, the flush takes the cuttings back to the surface in the annulus. So annular size and pump size or compressor size are closely related to make sure you're getting the right velocity to carry cuttings up the well. Right, this is the PDC bit. This is probably the biggest revolution that's never happened, to be honest. Fixed cutter bits, as I say, have been around since the very beginning of rotary drilling. What we're seeing now is 10 years ago, we would not have used these bits in anything harder than limestones, because the actual cutters didn't stay in place and they wore down very quickly. Nowadays, with the increased the way they're building these bits has allowed them to drill in very much higher strength rocks in granites, in particular in the Western USA. They've done a lot of work recently. And I do hear, lots of people say, "Oh, this is new technology." It's not new technology. It's old technology, newly applied, to be honest. So it has changed the way we're drilling granites. But whether we see the overall efficiencies that we're going to see from systems such as the Strada mud hammer remains to be seen. These are still early days, from probably 2 or 3 years now that we've been pushing these bits in a very different way. The downside of doing the PDC in harder formations is you need to apply lots of weight. Once you apply lots of weight, you've got extra mechanical energy going into the rock. They are drilling quicker, so you have to work out what's my cost of energy in and the time taken to get a true cost. They are very interesting, and I think, I can't be 100% sure, these bits, Ultra Lab, who I work with a great deal, they've developed the interesting bits for Strada. And again, if you reach out to either Julian or Taras, that they can give you a lot more information on that. The Ultra Lab guys, really great. They work with you very similar to the down the hole hammer bits. They can design the cutting structure to match your formation. So you're not getting, it's not an off-the-shelf bit. It's much more, this is going to solve my issues. They're very quick at redesigning if something doesn't work first time. It's a longer delay than you would get with a down the hole hammer bit, but it is very effective in being able to drill formations quickly and efficiently. And I'll say efficiently because that's very important. So it's worth, on the deeper holes, looking at the PDC. And as I say, in Western USA at the moment, on the Forge project in Utah, and I think there's a hole going on in Oregon at the moment, which is quite high temperature, 350 degrees, I think. They will be using PDC bits. That's just a slide from Ultra Lab showing on what, a particular section they drilled. So ROP of 14 meters an hour, roughly, that's good. This is, when you hear about traditional drilling in granites, you're talking 1 to 3 meters an hour. And I know from jumping back to Strada, they're getting sort of around 10 to 12 meters an hour on some very big hole size as well. So, and in granites, it brings tears to your eyes. Right, this is not actually a drilling technology, the sort of actual drilling technology that breaks rock. This is the RSS, the rotary steerable systems. This is really starting to revolutionize the geothermal drilling in particular. It's been around for a long, long time in oil and gas. The RSS is a development of the directional drilling systems. You can actually steer this. This is like driving your car almost. You can take it wherever you want to go. And you'll see on the end they're using a PDC bit, like the one before. And we can go from vertical to long horizontals, which elongates the sort of amount of rock that's exposed to the fluid that you want to heat and extract in a geothermal thing. For those of you, there's a company out there called Evil Technologies, and they are running what they call this underground radiator system, where they're drilling lots of very long horizontal sections and linking them all together so you have sort of long tubes. They are using RSS. One thing, it is an expensive method so you have to consider it as part of your overall sort of your overall drilling program. So that sort of covers off the sort of where we are with the technologies. They're not all of the technologies. We don't have time, and we could spend probably a day talking about each individual one as we go. But those are the key ones of, we're still using roller cones. We're still using down the hole hammers, either air or fluid, and we're now reutilizing PDC, fixed cutter bits in harder formations. So that covers off the sort of those sorts of technologies. And now we go into the non-mechanical. I'll be honest, there's no commercial non-mechanical technologies. I mean, there are companies there that are doing some drilling, but no one's drilled to great depths, and I say over 200 meters, 200 or 300 meters yet, with these non-mechanical technologies. All the ones we've been talking about them since the late 1960s, but they're still, they're not fully commercial. There's been a lot of research, and I'll show you in a minute on some of them. But how they leave a hole in the ground is still quite debatable. And when my good colleague and friend Pavel walks you through what we've done with laser experiments in the laboratory at the moment, you'll see, some of the issues that we're going to face with these non-mechanical technologies. But once solved, and they will be solved, with the ability to drill to these much greater depths, and these ultra deep 10 kilometers and 20 kilometers deep wells where the temperature is so high, the energy production is vast. And I've seen this thing that if we can only tap 1% of the Earth's geothermal energy, we have over 2,000 years worth of clean energy supply. So it's worth looking at, it's worth pursuing. We could carry on drilling with the mechanical methods to these depths, but as Luke said in his introduction, the time taken to keep pulling out and changing bits is going to make it cost prohibitive, not technically prohibitive. So this is why there's companies out there, and I'll talk through a couple of them in a minute. Why they're trying to pursue these rather more out there type of technologies. Thanks, Antonio. Right, these are in no particular order actually. Electro-pulse boring. This is where you put a high voltage shock and pulse it into the rock, and it sort of fractures the rock. It's a bit more technical than that, and I'll introduce you to a paper in a minute. There's a plasma technology that's currently a company called GA Drilling, which stands for Geothermal Anywhere. Hydrothermal spallation, super deep fusion drilling, which I have no idea what that means. Couldn't find anything on it, but it was mentioned in a paper in 1968. The microwave drilling, this is being made quite sort of topical by Quasi Energy, who were sort of planning to drill their 20-kilometer deep wells in 100 days. And then, of course, we've got the laser, and the laser is what Pavel will talk about in a few minutes. Next slide, please. So there's a reference there to a paper which talks through what electro-pulse boring is. They have drilled quite a few holes now to around 200 meters, The interesting thing is they're drilling quite large diameter wells. They're at 500 millimeters or half a meter diameter. So going deeper with electropulse boring could be very interesting because it can drill quite large holes and you can then flow much more fluid through these wells with lower pressure losses. And that's it. It applies an electropulse to the formation and then hence energy. And once you impact energy into the rock, it will change the status of the rock, break it up, and then you have to flush it away. So, but I do urge you to search out and find that paper. It's on it's open source now. So take a photograph of that, search it on the internet. It's very, very interesting. I think the paper is from 2012. It was a cooperation between some folks in Norway and Germany and China, I think. But it's well worth reading because it's like everything. If it works, it's going to be an amazing step forward. It's a long way from working yet, I think, commercially. So there we are. Next slide, please. Plasma technology, as I say, GA drilling. They're sort of they're pushing along with it, and they have been for a little while now. You can go onto their website, take a look. It's heating rock, with very high temperatures. How efficient it is, we don't know. It's difficult to say. It's been talked about since the late 1960s, but it's now starting to come. Is it commercial? We don't know. So, you can go on. Thanks, Antonio. Next. Then the microwave, and I have just a copy the verbatim from the Quaise Energy website. So they're using a gyrotron-powered drilling platform, and they evaporate the rock. So read into that what you will. They have been talking for a few years now about how they're going to drill some very, very deep wells. As I say, 20 kilometers. They're talking about 100 days, which would be very, very impressive. There's lots of things that we have to also consider when we are drilling much deeper, all the geomechanics of the rock, how the rock behaves when you drill a hole into rock that's being compressed under 12 kilometers of other rock. What's going to actually happen as you go into these much deeper formations. So, but as you see there, what they're doing, they're going to actually use conventional rotary drilling to get to basement. So that could be anywhere. And say in Cornwall, some of the basement is at surface. In the Baltic Shield in Scandinavia, it's at surface. Other parts of Europe, it can be at sort of 3,000 to 5,000 meters below the surface. So when they say they're going to use conventional, that depth range could change from 0 to 5,000, 6,000 meters. So again, just go onto their website and take a look, and then we come to laser drilling, which is what today is really wanting to look at, and the work that DeepU are doing, and the reasons why we're looking at lasers, because as we do go deeper, there's going to be a need to try and avoid using mechanical drilling methods, because of the sort of the physical restraints that we have with wearing things out. So that's my thing. And if you want anything, you can reach out through DeepU, or you can mostly if you Google me, you'll find me on LinkedIn, etc. Thanks, everyone. Thanks, Antonio.
Antonio, can you take back the division to switch to Pavel, please?
Thank you. Pavel, are you? Okay, thank you very much. Pavel, you are mute. Okay.
Okay.
Okay, Pavel, you can share now.
Okay.
If
Do you see the correct image?
Yes, okay.
Okay, great. Okay, and do you see the puncture? Okay. So thank you everybody for being here. My name is Paweł Słupski, and today I would like to share a little bit of our results from the DeepU project, and hopefully answer the question of if the drilling rocks with laser is possible, or it's still in the domain of science fiction. So let's start. Building up on what Kevin said about non-mechanical drilling techniques, generally most of those techniques work on the amount of energy that is delivered to the rock surface. And as already noticed in 1980, that we can distinguish two drilling regimes, one related to mechanical response of the rock called thermal spallation, or gradual heating up the rock, which leads to melting and further vaporization. And answering the question why to drill with a laser, not with plasma or other drilling techniques, I would like to mention a few advantages of the laser technology. Mainly that is its commercial availability, its modularity, that we can increase the power of laser. And generally, with comparison to other methods, we have almost no losses on the transmission, even to long distances, such as 4-kilometer depth. The main drawbacks of laser technology is low absorbance of radiation in the rocks of visible light. For instance, for granite is around 50% for fiber laser wavelength. The complicated optical system and the low efficiency for or claimed low efficiency for vaporization. However, it was not confirmed that the vapors may absorb that much energy that it will stop drilling. Most of those drawbacks were addressed in our project, and we all found the solution or understand better the mechanism so we can optimize the process. In our project, we use ytterbium fiber laser with a power range of 170 watts to 30 kilowatts at wavelength of 1070 and working in the continuous mode. Okay. And so what are the main laser rock interactions and what they are depends in the for the geological materials such as rocks? So we have absorption and reflection that are the most important parameters, as the ratio of those two controls amount of energy that actually being absorbed by the rock and can cause some interaction. So in case of granite, we have here around 54%. And there are, of course, secondary processes, scattering, transmission, but they do not play such a significant role in laser drilling. And then we have the parameters that actually control or affect the absorption rate, that is radiation wavelength, as shown here on this diagram. Of course, the angle of incident, surface roughness, and rock type that generally summarize all the characteristics of each rock. And finally, the laser rock interactions, the observable process depends on the rock's texture. That includes mainly grain size, mineral composition, chemical composition, that can be summarized in thermophysical properties of the lithology. But those parameters we can describe, we cannot do much about them, but what we can control is the power and irradiation time. So we were mainly focused to better understand the impact of those two parameters. So to understand how the rocks interact with a laser, we have designed 3 types of experiments: linear laser tracks that basically was the performing the constant irradiation alongside the track, with increasing the distance that effectively was reducing the power density delivered to the surface. So we could observe its effect on the rock, how the power density changed. Then the punctual test were mainly focused to understand the time, irradiation time effect on the laser drilling, and finally DeepU drill head tests. So the tests that we actually plan to solve the technological and technical problems to perforate the rocks. And the lithologies that we selected, we can divide in primary lithologies such as granite, sandstone, and limestone, that we investigated heavily with various experiments, techniques, and also characterized the rocks itself. And secondary lithologies as gneiss, basalt, and slate, and migmatite, that were used to verify very specific aspects of the interactions, and hope in the future we will also study them more. The methods that we used to investigate was infrared imaging, thermocamera for monitoring the laser drilling process, and for further understanding of the outcomes, we used photogrammetry to study the morphology of the craters, and generally for lacing products, the optical electron microscopy, and for chemical mineralogical composition, X-ray diffraction and X-ray fluorescence. So here we can see generally some of the results and outcomes of linear track tests and punctual track tests, and where we could observe the phenomena occurring depending on the power density, power, and the irradiation time. And what we were expecting is the initially start the spallation, then we are moving to the melting regime, and finally we can see the vaporization of the rock. However, we could notice, which is also well pronounced on the lacing product, where we can see well consolidated glass within the vaporization region. Then we can see some melting evidence. And as we reduce our power, effectively power density, we can see only spallation. However, close examination of the infrared imaging has demonstrated that all three processes often occur simultaneously, to different intensity. However, it has to be acknowledged that here we are dealing, depending on the lithology, with some overlap. So the final result of this series of the experiments was attempt to construct process diagrams for granite, sandstone, and limestone, as we can see here. And on the y-axis, we can see power density in logarithmic scale, so ranging from 100 to 1 million watts per centimeter squared, and diameter of the beam. So the gray area on the graph is showing our power range accessible with our laser. Stars representing the punctual experiment, while dashed lines representing the linear track experiments. And very quickly with this, we could identify the power densities necessary to obtain spallation, melting, vaporization, and vaporization for granite, spallation and vaporization for sandstone, and also the same processes in limestone. All with their minimum power density necessary to obtain. And what we can see here that generally granite is relatively easy to melt. We can see that our quartz-rich sandstone generally spall even at very high power density, while limestone need much more power density even to initiate the spallation and at higher ranges melting. So what are the implications of this process diagrams? They are actually the possibilities of application lasers to drill useful boreholes. For instance, at the moment, we managed to drill approximately 10 centimeters. We are able to drill around 10 centimeters borehole within this range. As we can see, the black line that corresponds to our current maximum power output. And therefore, we are planning to increase the power to 120 kilowatts, which will allow us to drill with thermal spallation. In that case, the diameters to around 20, even higher. However, when we consider the melting vaporization process, as we can see, even at extremely high powers, such as 1 megawatt, it will be very difficult to drill useful diameters with a laser. So at the moment, the melting and vaporization require much more power that is available. Therefore, we cannot expect soon to drill useful diameters for geothermal purposes. So just to summarize the melting and vaporization drilling process, we can see here the melting spallation, the ER record of melting of laser drilling in melting spallation field. We can see the pulses as the rock heats up, evaporate, and then we have rapid event of spallation. And here on the right side, we can see the temperature versus irradiation time for two experiments. And what we can see from those temperature record diagrams that that temperature of the melting process can be divided in three stages. Steep stage, that we have very rapid heating up of the surface. We have the gentle stage when the melting already was partially initiated and the latent heat has to be fulfilled. It's the energy is consuming for the latent heat of the rock, and eventually the rock is completely melted, leading to formation of balanced temperature that stabilize after around 40 seconds, usually for each lithology, and it depends on the rock type and power of the laser, and which generally means that we can control the temperature of this balance melt by changing the laser power. Yes. And the results, the lasing products of melting vaporization drilling, as we can see here on the side view or cross section of such a borehole. Here we can see top view, so there is the beam. We can see glassy vitrified layer and the granite on the top. So mainly that the vitrification of walls is possible with this type of laser drilling with melting vaporization. The layer of glass, the vitrified one, in the case of our experiments, was about 5 to 10 millimeter thick. And we have, knowing the composition of that glass, we could calculate the viscosity of the granitic melt. So we can see on the right side the temperature versus viscosity, and around about 10 to power of 12 pascals second, we can, as we have estimated the glass transition temperature, so that temperature is the temperature that we would have to cool down the our molten borehole walls to quench it and vitrify the layer. A little bit more observation on the glass itself, that it's heterogeneous. It's as I mentioned, heterogeneous, so you can see that it's not necessarily completely homogeneous. That it may contain relics of unmolten phases, as we can see in quartz. That this melt often fulfills and completely filling the fractured form, doing some spallation still present in the rock, basically sealing it's improving the porosity. And it might also contain solid phases that crystallize during the quenching, such as microlights in that case of magnetite. And the main question is what are the mechanical properties of such a laser-generated glass? We still haven't investigated that. And if laser-generated glass can substitute borehole casing. As we know, the glass, it's known for its very high uniaxial compressive strength. However, due to its complexity, it's very difficult to model. So we would try to address this question in the future. And right now we switch the drilling regime to thermal spallation laser drilling that we already established. That is the most likely the most useful process for drilling of larger boreholes. So we have designed this DeepU laser system. That main aspects, or most important aspects of the system, is divergent beam that we have. We can see that thanks to that we can drill larger diameters than the drill head itself, and we are using nitrogen flushing system to remove the particles from the borehole walls and further transport it to the surface. And here we can see the video of the drilling itself. That's the spallation of granite. And on the right side head, we can see the complete analysis of with the ER image from the top with heterogeneous temperature. We can see 15 seconds craters generated by thermal spallation. They are characterized by very clean cut surface. And we also observe the temperature and establish the balanced temperature for thermal spallation for each lithology. And it's important to notice that according to the previously shown diagrams, we miss power to activate or initiate the thermal spallation in dry limestone that leads to the subsequent melting and very low penetration. Therefore, we tried with H2O saturated limestone, and we were able to thermally spall it at very low average temperature. Then we had to also understand how to remove, what to do with the spalls that are removed during the drilling thermal spallation regime. So we have collected the spall particles of each lithologies. We have prepared the epoxy samples, and further we have investigated it under the electron microscope. We can see here those images where the size distribution, the sphericity, roundness, and generally shape, composition. As we can see in case of granite, we can also see some droplets of glass, and we could calculate we could estimate the possibility to how to efficiently remove those particles. And I believe in next presentation, Professor Maciej Chorowski will a little bit more talk about that aspect. How to sustain thermal spallation and stable penetration? The most important aspect basically is the efficient flushing system, as drilling with thermal spallation usually demands drilling at as possibly highest power density. Therefore, the particles, if they will be trapped at the bottom of the drilled borehole, may eventually melt, leading to a formation of glass, or in the extreme cases of melt pool at the bottom that is in its liquid form is highly reflective for the radiation, and basically change the drilling regime from thermal spallation to melting, and effectively stop the penetration via thermal spallation. So that is the importance of the flushing system. And what actually happens with the rock itself? I said that in macroscopically it's very clear, nice clean cut. And however, at the electron microscope, we can see the number of shearing fractures generated very close to the crater surface. Here we can see the bottom of the borehole in granite, sandstone, and limestone, and we can see that those shearing fractures that are parallel to the borehole walls, they reach maximum 1 millimeter in depth into the rock. Therefore, the thermal spallation does not affect the thermophysical properties of rocks, or at least we were not able to detect such a change with our current instruments. So a few words about the efficiency of laser drilling. We have used to put some parameters, the rate of penetration that is defined by the depth of the borehole divided by the irradiation time, and also specific energy, power multiplied by irradiation time per volume of the rock that was removed. And in that case, we have to underline that this specific energy can be used at this moment only for fiber laser drilling, as it wasn't normalized and corrected for the absorbance reflectance ratio, which I was mentioning in the beginning. So looking at our estimations or our experiments performed for thermal spallation performed with 5 centimeters diameter of borehole, we can reach rate of penetration around 10 meters per hour for granite, around 15 meters for sandstone, and for wet limestone we have around 5 meters per hour, and we can see very significant drop in the dry limestone. As I mentioned, it's related to not sufficient power to initiate thermal spallation. Therefore, we have melting, and we have much higher specific energy and low rate of penetration. Meantime, drilling with melting vaporization for 1 centimeter diameter, we can see very low penetration rates. And the exceptions here is sandstone, but here close examinations of infrared imaging revealed that spallation is still contributing significantly to the removed materials, so it's not performed purely by vaporization in that case. So quickly to summarize visually summarize our results, we have laser drilling. We may work on in two different regimes: melting vaporization and thermal spallation. Therefore, we can propose two different setups or two different technological solutions. The thermal related to thermal spallation that we currently can successfully apply for the drilling purposes, and the melting vaporization that probably is the matter of the future, as we need significantly much more power to drill larger diameters. However, both of those techniques have their advantages and disadvantages, such as vitrified layer for melting and a very high rate of penetrations for thermal spallation. So the main conclusion is, answering the title question, the drilling rocks with laser is possible. It's not anymore the science fiction. However, at the moment, the main regime is thermal laser-induced thermal spallation that provide rock penetration, and melting vaporization is much more demanding energetically. However, it can provide or form vitrified layer that can work as casings in the future for some selected lithologies. And we have successfully tested at laboratory scale the DeepU laser drilling setup, and looking forward to continue this work in the field and verify to develop further this the drilling system. Thank you for your attention, and I would like to leave you with this beautiful mosaic of minerals under the polarization microscope, where the black represent the glass. Therefore, we are looking at the vitrified layer in granite. Thank you.
Thank you, Pavel. Now we link directly to Maciej Korowski, is a colleague from the University of Wrocław, University of Science and Technology in Poland. We'll talk about the use of cryogenic gas for coupled with the laser for drill. Thank you, Maciej. And we have 15 minutes delay. If the following pattern can reduce, if it's possible.
Yes, thanks
Thank
for
you,
this.
Maciej. Thank you.
Thanks for this introduction. I will try to make my presentation short because it is following some suggestions and conclusions from the previous ones, which were very informative. So first of all, we would like to focus on laser during cryogenic system, and with some about very short discussions concerning why cryogen, what are the process requirements, how to design the process of the cryogenic supply, and what are the mechanical challenges, and finally what can go wrong in such robust but nevertheless still complicated system as we would like to propose. First of all, what we see is that to be efficient with flushing, and Pavel stressed very strong that it is very important to remove all the cuttings from the bottom of the borehole. We have to supply fluid and we have to remove it. After some basic considerations concerning the thermodynamics nature of the flushing fluid, safety of the operation, chemical stability of the gas to be used or chemical compound to be used, finally we decided to go for cold nitrogen, so cryogenic nitrogen. and it has been chosen as the most suitable candidate for flushing medium. What does it mean? That from the surface we have to deliver the cryogenic nitrogen down the borehole up to several kilometers to turn its direction, to remove some heat, to be able to remove the cuttings from the bottom and to take them to the surface. So it's a multi-purpose task for this cryogen. And it's not only the nitrogen that was chosen, but also it has to be decided what should be the entrance parameters of this gas. Taking into account that we first have to have the flushing medium with a sufficiently low temperature to be able to accommodate heat. The direction is cryogenic. Cryogenic means the temperature, well, something like 120, maybe even less Kelvin. In Celsius, it is minus 250 or even more. Liquid nitrogen could be a good choice, but it will not be possible to keep it in this two-phase thermodynamic state if the pressures are going to exceed of about 30 bar. So, we can expect such high pressures or even much higher pressures down the borehole during to hydrostatic pressure and during to pressure drop in the return channel. So the only choice, reasonable choice, is supercritical state. Supercritical means single phase, high density, low temperature, but not well defined, because as a single phase we do not have a temperature stable, and we add some heat, it will go up. So supercritical is not a point like, it's rather a region. And we see that we go towards higher pressures, even to several hundreds. So supercritical nitrogen was proposed since it meets all requirements and simplifies the system through single phase flow along the whole channel. We do not have to use phase separators. We do not care for two-phase flow. We do not care for heat transfer coefficients, which are difficult to identify for two-phase flow. We do not care for two-phase flow pattern. We go for a simple system, but nevertheless, from technical point, very challenging. Why? First of all, we have started to analyze what will be the pressure that will allow us to go for relatively deep borehole. With a quite sophisticated numerical model that was elaborated by my colleagues at the university, we are able to indicate, for instance, for a given pressure down the down of borehole, the maximum depth. So you see, if you would like to keep 30 bar, we would definitely not go for a deeper than something like 3,000 maybe meters. And it also is depending on the particle sphericity and particle diameter, because we found that from the required mass flow, the highest requirements come from the necessity to take the cuttings up to the surface. So if we fulfill the requirement that we have sufficient return flow to take the cuttings, we also by definition fulfill the requirements for the cooling down and recovering all the heat. So that is to demonstrate that we control the required amount of nitrogen to be circulated through this system with respect to the nature of the cuttings that are to be removed, and also with respect to the diameter and depth of the borehole. And well, it has been demonstrated by modeling that supercritical nitrogen is essential to maintain an adequate mass flow rate despite significant pressure drops in small process pipes and to prevent the formation of two-phase flow. So it seems that it should work even for very deep holes reaching over 4,000 meters. Nevertheless, as in any modeling, we had to take into account many assumptions. We have decided to construct a dedicated test rig to test the model. Here you see the warm part of it. It will be used, or it is now under final stage of commissioning, so it is already in use, to check first of all the transport properties of debris, of cuttings, and to check if the model is adequate and can be used as a reliable source of information, what is a really required nitrogen flow through the system. So our methodology is to model, to calculate, and to validate the model, at least for the basic input parameters. When we look at the system, cryogenic system, well, it starts from the source of liquid nitrogen, because what you find on the market is liquid nitrogen. We remember that we are not talking about peanuts, because we will require something like about 3 or even 4 or 5 kilograms of liquid nitrogen per second, which means that it is really something like tons per hour and tens of tons per day. So it must be industrial system. So we supply either from a separation unit or from delivery by trucks. We store it in liquid form. We compress to required pressure by cryogenic pump. As we compress the fluid, it is not high energy consuming device. Roughly speaking, we consume something like between 5 and 10% of energy that would be required to compress gaseous nitrogen. So we save energy because we compress fluid. It is still at low temperature if this compression is in adiabatic condition. We go to the drill string and we go down with this supercritical nitrogen with the temperature of about 120 K with pressure. We have calculated that having the very deep boreholes and having to assure sufficient nitrogen to remove the cuttings and sufficient also to withstand the pressure drops during the return in the return channel, we can expect that the pressures, working pressures, will be up to 350 bars. So high pressure, relatively high pressure industrial installation. And now we are coming to basic, I would say, technical challenges and some innovative solutions that have to be proposed in cryogenic engineering, because it is not a big amount of cryogen to be supplied for cryogenics, something like kilograms per second. We have it in industrial applications. The length of the transfer lines of kilometers are also not exceeding the state-of-art technology. But what is completely new here, that we are going down the borehole. So we have to use the channel here denoted as blue line, supplying high pressure nitrogen, so robust with sufficient mechanical stability. It is proposed to be a spiral one, so self-compensating. We avoid the necessity of using the bellows. We are not able to avoid it in case of laser beam pipe with optics due to different thermal contractions depending on the temperature. The return annulus channel will be separated thermally by vacuum insulation. So we have to incorporate high mechanical stability of input channel, vacuum insulation, return channel with the ability to take the cuttings. And what is, I think, the most difficult part of this proposal is the coupling, because to go down several 100 meters or even several kilometers, it would not be possible to with a single piece of pipe. So having it sectorized, we have to use several tens or even several hundreds of couplings along the borehole. The coupling should be robust, tight, easy to fix, not very sophisticated, so to stay reliable. And if we would like to summarize the challenges, so we have to withstand low temperature, materials must retain the key properties even at cryogenic temperature. So we are limited to some categories of materials that can be used, roughly speaking, for the temperatures characteristic for liquid nitrogen or supercritical nitrogen. We have to cope with heat loads. So the design should minimize direct and short connections between cryogenic and room temperature components. Especially, we have to insulate and to reduce to minimum. Perfectly, it would be to reduce to zero heat flux from the beam pipe to the supplied nitrogen. We have to use, because it was not possible to find a sufficient low conductive material to fulfill the requirements. So we have to go to the vacuum insulation. So we stay with vacuum insulation. It will be vacuum powder insulation. Nevertheless, we have to guarantee vacuum along the pipe. We have to withstand mechanical load because of significant pressure and self-weight of the system. And finally, it should be economically feasible. So materials should be available and easy to work with, we should not go to very sophisticated rocket science materials that maybe exist but are definitely too costly to be used in any application on this scale and to compete with other industrial concepts of drilling. So coming to the end of my presentation, here I would like to present a very primary concept of coupling, and it is a cross-section of the proposed channel or system to supply liquid or supercritical nitrogen down the borehole. Here you do not see its spirality because it's a very short cross-section. In the center, we see beam tube. It is separated by vacuum separation. We also have to deliver electricity down the borehole. So we have to design also electrical feed-throughs, which will be both tight and robust. We have to guarantee fast coupling. We have to guarantee sealing with some special system of the sockets. So what we believe that we should be able to propose leak-tight sealing feasible for cryogenic temperatures and for such a robust system. The system we should be characterized by mechanical strengths. It should be possible and usable for fast and robust assembly, and characterized by low thermal load to supply the low enthalpy of the incoming gas and to make it a suitable both cooling medium and later, after some warm up, a good medium for pneumatic transport of the cuttings to the surface. This is also to be prototyped. The prototype is now under final stage of fabrication, and we will be able till the end of the project to test it from mechanical but also cryogenic point of view. What will be prototyped? Not a very long drilling pipe, but just this coupling with some endings, because it is the most vital component of the proposed system. Well, in cryogenics, as it is the technology that is combining the fluids that in case of uncontrolled heat flux can expand even 1000 times, so and creating danger pressures. We have also analyzed what can go wrong. Here you see some events that can be described as a loss of vacuum due to either process pipe break, number one, so cryogenic fluid leaks into the vacuum space and we have rapid heat flux to cryogen still being in the pipe and pressure increase. Laser pipe break, casing pipe break. Each failure mode is to be modeled and analyzed with respect to its potential consequences, and proper mitigation actions were proposed for each identified failure scenarios. Mitigation actions means either something can be improved by the design, or some procedures are to be elaborated how to react, not to block the system and not to lose the channel and not to lose the equipment and not to jeopardize the people working with this relatively non-explosive, but also accumulating a lot of energy that can be converted into explosion-like chemical or physical blasting gases. Coming to the conclusion, well, we believe that cryogenics technology, materials, procedures is well prepared to deliver cold nitrogen down the deep borehole. Thanks for your attention.
Thank you, Maciej. Very interesting. A lot of problems are solved, but other in the next months, I hope. We quite go to Riccardo Pasquali from GeoServe, Ireland, regarding the environmental regulatory aspects that complete this webinar. And I play Riccardo the sharing of his.
Good morning, everybody. Can you see the screen?
Yes, thanks.
Okay, brilliant. So good morning or afternoon, should I say, everyone. So what I wanted to speak a little bit about during the course of this, the next 10 minutes really are, you've heard a lot about the DeepU technology in this webinar this morning. And there is a lot of innovation, of new methods in which we're looking at drilling and considering drilling, but obviously the ultimate path in terms of trying to get new drilling technologies is one of getting these to actual commercialization and getting them to wider use out in the field. So there is an element, of course, that needs to be addressed, which is the sort of the legislative and regulatory requirements and the environmental aspects that are associated with drilling projects. And really, what we want to cover this morning is just obviously this is quite a wide topic, and I will come back to some of the aspects of why that is at the moment that we needed to cover in the project. But what we wanted to see really was to, first of all, have a look at the conventional methods of, let's say, regulating and legislating for deep drilling operations, and looking at the systems and the processes that are associated with that legislation and regulation, and compare those in terms of what you have heard today in terms of the new technology solutions, in order to see, broadly, does it fit, or does it, are some changes in our processes required in order to basically allow us to progress to the next stage. So to sort of frame the context of the discussion, we were really interested, all of the partners in the project, to try and understand, what aspects would a regulator or a legislator of drilling operations want to home on in terms of the DeepU technology. So obviously you can see, but as you've heard this morning, both from Pavel and Professor Shorowski, there are some significant innovations in the actual process of the DeepU drilling compared to what is out in the market there. There are some fundamentally different EHS risks associated with managing the processes of both the laser drilling and the cryogenic system, which need to be considered. And we wanted to try and understand, if we were to present this technology to a regulator, what would they be looking for in terms of gaining acceptance to the technology, and what would be required in terms of implementing it and bringing the technology to the field in real in real type scenarios, so on real drill sites. So effectively, this diagram is kind of a high-level summary of trying to understand how we approach the problem. Well, the first was to try and understand the technology developments, which you have heard about this morning. But as you've also heard from Professor Shorowski a few moments ago, these are very much still evolving. So there's still a lot of prototyping and testing going on. So all of the questions are not yet answered, but this is broadly the process that we followed. So looking at the technology developments and then comparing those with high-level compliance challenges in terms of legislation and regulation principles, to see if the technology could actually be used out in the open market. So our challenges, I won't spend a lot of time on this slide because I think you've heard a lot of the material already this morning. So obviously the use of industrial scale lasers, and particularly relating to the drilling side of things in an uncontrolled or changing operational environment. So this is the juxtaposition between using industrial lasers in a controlled laboratory situation compared to a drill site. The inclusion of cryogenic fluids as part of the drilling process to flush the cuttings and clean out the wellbore. Then the third aspect, which is actually a really important one, which the consortium have been doing quite a lot of work on at the moment as well, is trying to understand, how do you maintain hole integrity and how the borehole at great depths would perform over the operational, let's say, lifetime of the system. So the fourth challenge really is trying to integrate all of these aspects into existing drilling equipment, practices, skill sets, and looking sort of at the broader drilling market and trying to understand how DeepU could be integrated. So if we go to the first one, really, which is just sort of, I suppose, the fundamentals, we've called it here, of drilling legislation and regulation. And this is a sort of a catch-all diagram to demonstrate the key aspects in terms of deep geothermal drilling that you would expect to have to address in any deep geothermal project, pretty much irrespective of what jurisdiction it's in. So you have your licensing requirements on the left-hand side. You obviously have to comply with health and safety regulations and requirements. There is environmental protection for the drilling operations, and then the lifetime of the system. And then during the operational phase, once you're effectively completed, in terms of the geothermal resource, you also have to have a resource management plan. So you need to be able to demonstrate how you would how your system would perform in the long term. So if we focus a little bit on the drilling aspects, you can see here on the slide, you've got the general operational health and safety licensing requirements, the process safety management and safety management systems that you would put in place for any drilling operations. You've got leading indicators in terms of developing a safety culture of practices, and then how you would, report incidents or manage incidents, and have an emergency response plan. And effectively, this is a pretty standard tree across many jurisdictions, and it's all based on a hierarchy of controls for safety management, which starts with eliminating hazards early on in the design process, and trying not to get basically to the lower section of this overturned triangle, which effectively is mitigate and respond. So generally in a process safety management system, when you get to the base of the triangle, it's probably a little bit too late. So as you've heard, our technology is still evolving, and we want to make sure that we maximize our opportunity to eliminate and prevent effectively and put in place the most effective process safety management strategies. So what we did during the course of the project is look at a number of jurisdictions across Europe. You can see them listed there on the left-hand side, and tried to look at the general principles of legislation and regulation for geothermal systems, and giving a sort of a comparison in terms of what aspects of the drilling operations, first of all, would have to be considered. And what we've done with that is we've managed to sort of summarize this again in this diagram that you can see on the screen. And I'm not going to cover all of the aspects, but you can see that in the orange boxes, there is exploration, production, and abandonment. But as part of exploration and production, there are significant components related to well planning, drilling operations management, well engineering, test drilling, and then obviously completion and environmental monitoring during the course of the drilling operations, and the production aspect, as well as obviously abandonment once the system is complete. So it was very key for us to try and understand these broad lines of processes, and then look as the project evolved and the DeepU technology evolved, how do we fit in there? So environmental health and safety indicators were one of the key items we wanted to consider. And you can see here this diagram from the UK HSE showing sort of lagging and leading indicators. And the point really in relation to this diagram is we need to define, as part of I would say nearly all of these new innovative technologies that you've heard talked about, particularly by Kevin this morning, but more importantly For DeepU, you need to provide these leading indicators that are on the right-hand side of the screen. So you need to be able to provide operational procedures and sensible drilling practices that are accepted and are recognized by legislators and regulators with a system that minimizes, your response-related let's say indicators, which are down on the left hand side, and you can see there are gas kicks there, or blowouts and so on and so forth that are highlighted. So if we take those high level topics and we try and compare what is available in terms of conventional drilling and the DeepU methods, the DeepU processes, which I will come back on in a few minutes. You can see some of those EHS indicators on the left-hand side of the screen. And unsurprisingly, for conventional drilling, if you look across the jurisdictions, there is quite extensive guidance on many of the aspects, such as general operational health and safety, drilling program design or well control measures. These are just some of the ones that we've highlighted here today. But if you then look at the right-hand side of the table and consider those EHS indicator aspects with the technology that you've heard about this morning, there is quite a bit of work to be done yet in terms of finalizing how those are addressed. So, for example, the operational health and safety practices associated with DeepU, I will talk about the processes in a minute, are present because the various, let's say, industrial processes that are being put together to form the DeepU technology are obviously regulated and have very good health and safety practices, but they are not necessarily regulated or set in the context of a drilling environment. So there is some work yet to be done on those. There is a huge amount of work to be done in terms of training and certification for both equipment and personnel, and I will touch on the equipment in a few moments. But you can obviously see that somebody who is trained to operate a laser is not obviously necessarily going to know anything about drilling or have any training in relation to drill sites and drill site management. There is a need to develop additional measures in terms of well control procedures and barriers, which we're working on, and also the other big one to highlight is obviously the emergency response plan. And you've heard from Professor Shurovsky and his team's risk assessment in terms of the cryogenics and on the use of the laser in the drill string, that there are effectively other risks there that probably don't occur in the context of conventional drilling technologies. So I will just bring you to my last slide here, which is just highlights some of the topics that we are considering. So, for example, the use of the laser system requires a specific fail-safe operational procedure that is, applicable to a drill site, and in particular the use of the methodology for connecting and disconnecting the drill string, starting and stopping the laser, for example. In terms of the nitrogen system, there are operational procedures for how it will be used and stored on site, and how the process will integrate into the drilling and flushing. And there are also some optimizations to be done in terms of defining the right method for separating the cuttings and considering the emissions. So you've heard today from Pavel some of the sizes of the potentially the drill cuttings that would be produced. So a dedicated system would have to be developed as part of this. In terms of the drill string, there's obviously a very innovative design that you saw in the last presentations of how the drill string is put together, how the connections are implemented, and what the materials and specifications are for that drill string prototype. So there is a certain amount of certification and standardization that will be required with respect to that to try and align it with, let's say the broader deep drilling sector. So in terms of electrical infrastructure on power supply, this is a consideration at the moment. Obviously, the laser will require a certain amount of electrical power connection. So that is another aspect that is being considered. And then we will need, very clear, well-designed methodologies, for example, in consideration of the borehole completions and the lithologies. And if you think back at the aspects that I highlighted earlier on, so to demonstrate to the regulator that you have environmental compliance using the DeepU drilling technology in certain areas, we would have to, perhaps consider a multi-method approach in order to allow the protection of aquifers and drinking water areas in the shallow sections of the boreholes. So all of these are items that are still being considered and will be refined towards the last part of the project. So I can see that the time is racing on. So this is my last slide, Antonio. So maybe I will stop sharing now.
Okay, thank you very much to you and to all other colleagues, partners of the project. We have some minutes for question and answer. I remember that all the presentation will be uploaded in the webpage of the DeepU project on Monday next. And if you have some particular questions, it's possible to connect directly with the experts. But if some of you likes to clear some aspects or to have some question directly to the conveners, could be possible now. Thank you.